I want to talk about waves. Waves are pretty awesome, and they follow naturally from simple harmonic motion. I want to point out to you that we've been discussing position as a function of time. For a simple harmonic oscillator, we say that it's doing something like this, starting at some position and going in a cosinusoidal fashion like this. And we've identified things on this graph, like, for instance, this is the amount of time that it takes for a complete cycle to occur, and we call that a period. And we've also called this distance right here an amplitude. Cool. And from the period we've calculated frequency because it's just 1 over period. And now if you have something that is simple harmonic oscillating, if it is oscillating in simple harmonic motion, a mass on a spring, for instance, or what if I attached a marker to a pendulum? That marker would go like this. It would go shoo, 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 shoo. Can you imagine what would happen? I'm going to take it down here just a little bit. Imagine what would happen if I took a marker and I let it go shoo, 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 and at the same time I slid the paper to the left. Now this is going to be kind of a risky thing because it's not at all I'm not at all guaranteeing that I can create simple harmonic motion, but I want to pretend that I could do something like this. Shoo, 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 shoo. Do you see that it does kind of look like, oh man, it looks like an actual sine wave in space. So now we've got something a little bit different. I'm going to try to draw some axes on this and say that this is position maybe in the y direction versus position, let's say, in the x direction. So now, oh man, now we've got different things to define. This distance, this is a distance, no longer a time. So it's not period. This distance right here, oh, this though, ooh, this still is the amplitude. What should we make of this distance right here? It's the distance between two crests of a wave. Here we've got a crest defined, and here we've got a trough. It's the distance between two crests of a wave. What do you want to call that? It's sort of like how long the wave is. So yeah, me too. I want to call it the wavelength. And we'll use the letter lambda to represent that. Wavelength is lambda. Now look how similar these graphs are. In fact, they're absolutely identical. So I want you to notice though that the axis here is time. So of course if we're measuring horizontally on it, we're going to get a time, and that will be the characteristic time for the system, the period. And here we're going to get a distance. That's the characteristic distance of the wave that we've created, and that's going to be the wavelength. All right? Now it's time for us to relate wavelength and period and frequency and all of those things. So I want to know more about this wavelength idea. So over here, I ask you to consider what speed means. Speed is, of course, distance over time, right? So we'll write delta x over delta t, and we'll say that, oh man, the wave goes one wavelength in some time, right? So how long does it take a wave to travel by one wavelength? Well, let's think again about our oscillating pendulum. How long does it take to go one wavelength? What that means is if the wave, if the paper, in the language I was using, if the paper has moved by one wavelength, how much time has gone by? I'm going to do that one more time. If the paper moves by one wavelength, how much time went by for the pendulum? Well, it's the same amount of time. It's that period. This is a very subtle thing. If the paper has moved by a wavelength, then the time that took is one period. So I'm going to write down the most important wave equation there is right there, and you can figure it out on your own again if you need to. This says that speed is wavelength divided by period. And you know what 1 over period is, right? So this means that speed is wavelength times frequency. All right? All right, good. So let's put that in a little box. It's pretty darn important. V is lambda times F. Check the units on that. I've got units of, let's go to blue, units of meters per second equal units of meters, that's the wavelength, units, and units of frequency, which is 1/seconds, or hertz. Oh yeah, okay, so that works out. Everything's fine. In fact, that system of dimensional analysis is a very useful system, and we're going to use it all the time. I guess the next thing that I'm wondering is how fast does a wave travel through a material? How can we get a handle on how fast the wave actually goes through a material? Let's sort of identify what kinds of things it might depend on. Let's see. I think if you imagine holding a rope, you can believe me that the tighter you pull the rope, the faster that wave will go. If you pluck that rope, then the wave, if you're holding it really tight, the wave will go pshh. But if you have a loose rope, it's kind of dangly and catenary curve and all this nonsense, you go pluck, and the wave goes doo. And so it probably depends on tension. We could call that, what do you want to call that? The force of tension. You might call it a capital T, but that might be really confusing with your capital T up there. So we might say it depends on the tension. We might also say it depends on how massive the rope is. Of course, because the rope's mass is determined, it determines its inertia, and that will determine all kinds of things about speed. More inertia probably means a slower speed. All right, so let's see. If we've got tension force and the mass of the rope, but wait, if two ropes have the same mass and one is only 1 meter long and the other is 100 meters long, they definitely wouldn't have the same speed. We're probably interested more in thinking about mass divided by length, some sort of take a section of the rope that's always 1 meter long or something. What is the mass of a fixed length section? And the way to do that is to define something called, well, I'll call it mu, and it's going to be the mass, total mass of the rope, divided by the length, total length of the rope. Is that all right with you? In this case, mu is not dimensionless. Now it's got dimensions, it's got units, kilograms divided by meters. All right, so let's try to figure out what speed is. And I'm going to do this in a fun method called dimensional analysis. So I'm saying speed depends on tension force and mu, which is mass per length, and I argue that we can find this by dimensional analysis alone. So let's set this up. I want you to try this. I'm going to ask you to pause the video pretty soon and see if you can figure this sucker out. So we say that V is equal to, well, I guess it's going to be the force of tension to some power, we could call it A, right? And it's going to be multiplied by mu to some power, which we could call B. And we need the units to work out. So this is going to be meters per second, and this is going to be, oh, we've got newtons in here. Newtons are kilogram meters per second square to the A. And then we got this mu thing, which has units of kilograms divided by meters to the B. Can you find A, lowercase a, and lowercase b? Good luck. Pause. Got it? Got it? Did you find it? Well, here's what I'm thinking. I'm thinking we can't have second squared, and the only way to get rid of second squared is to take the square root. So I think that A might be a half. Let's play with that for just a moment. This is not the strongest way of getting through it, but it was the first thing that caught my mind just now. And when you're doing dimensional analysis, that's our skill that we're focusing on right now, dimensional analysis, when you're doing this procedure, you can kind of go haphazardly, or you can do it scientifically. Now, of course, if we're doing it scientifically, we would say that the power of m has to be 1 and the power of s has to be -1, and it would be very straightforward how to do this. But I'm going to go at it haphazardly. I'm going to say that meters per second must be equal to, well, I'm going to say kilograms scruted and meters scruted divided by seconds. Now you see how I've taken care of this side over this seconds right there. And then I'm still going to leave this as kilograms per meters to the b. Now what do I have to do? I have to get rid of this kilogram scruted. The only way to get rid of the kilogram scruted is to have b be a negative number. Let me point out here that I assert a equals 1/2 there, because I'm scruting this thing. Now I'm going to say that I need to get rid of the kilograms scruted. So I want, let's say, try b equals -1/2. I want to put a kilogram scruted in the denominator. So let's try that out. If we put meters per second equals, now I've still got all this pink stuff, it's going to be the scrut of kilograms times the scrut of meters divided by seconds. And I want to invert this sucker and scrut it. Now I'm going to say that's the scrut of meters divided by the scrut of kilograms. It's perfect. It's perfect. Look at it. Look at this. Meters cancel meters. No, just kidding. Kilograms cancel kilograms. And the meters combine to give me meters per second. So we have derived an equation. Let's go back up to the top where we've got these two statements. We've got a is 1/2 and b is -1/2, and we take these guys and we get our equation. Here's our equation. It says V is, well, I'm supposed to scrut the tension force, and I'm supposed to inverse scrut mu. There we go. Now, this is from dimensional analysis, so we know if these are the only things that speed depends on, then this is true except for any constants that might multiply it. Like we could have a pi in here, or we could have a 2 in the denominator, who knows, right? But we know it kind of has this feel. In fact, this turns out to be totally true. Totally. Can't really write today, but it is totally true and everything's cool. Before I completely abandon this discussion of the speed, I want to write this equation here and think about it for just a little bit longer. I'm saying that speed is the force of tension divided by mu, and I want to encourage you to see if this makes sense. The tighter I'm pulling the rope, the faster the wave will go. But the more massive the rope is, the slower the wave will go. Okay, so that kind of makes sense. I wanted to just throw out a couple comparisons for you. You know the speed of waves in air is actually called the speed of sound. And the speed of sound in air is about 330 meters per second. Now, that's cool, but I could give you a couple more bits of data to see how this makes sense. Let's see, the speed of waves, again, it's going to be sound because that's what is happening through a material like this. The speed of waves in steel. Now, steel has dramatically more mass, but it's also much more tightly bound than air is. So we can look at this equation and see if we can make some sense of it. But I will tell you that sound travels much, much, much faster in steel. The number that I've got is 5,960 meters per second. Wow. Also, I should point out that the speed of waves in aluminum. And what is the characteristic of aluminum as compared to steel? Well, it's much, much less dense. So the speed of waves in aluminum is 6,420 meters per second. So let's see if this makes sense. It is hard for me to justify why steel is so much faster than air because I don't quite know the bonding strength, that's this tension force, how tightly the steel is squeezed to the other particles of steel. But I do kind of notice that when I go like this through air, it doesn't really hurt. So it's not that much of a binding in air because I can slice through it. But when I hit steel with my hand like that, it hurts a lot, which indicates probably that the steel is really strongly bound together. But we can certainly compare these two right here. If we've got similar binding strength but a much less dense material, the aluminum, then I'm going to say that maybe the numerator is kind of the same, but for a stronger, what am I trying to say? Oh yeah, a less dense material, the aluminum is a less dense material, so V ends up being faster. Okay, so that's all right. And I guess, no, that's fine. We'll leave it right there. Like this, and we've identified things on this graph, like, for instance, this is the amount of time that it takes for a complete cycle to occur, and we call that a period. And we've also called this distance right here an amplitude. Cool. And from the period we've calculated frequency because it's just 1 over period. And now if you have something, slid the paper to the left. Now this is going to be kind of a risky thing because it's not at all a I'm not at all guaranteeing that I can create simple harmonic motion, but I want to pretend that I could do something like this. Do you see that it does kind of look like, oh man, it looks like that is simple harmonic oscillating. If it is oscillating in simple harmonic motion, a mass on a spring, for instance, or what if I attached a marker to a pendulum? That marker would go like this. It would go shoo, 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 shoo. Can you imagine what would happen? I'm going to take it down here just a little bit. Imagine what would happen if I took a marker and I let it go shoo, shoo, shoo. And at the same time, I want to talk about waves. Waves are pretty awesome, and they follow naturally from simple harmonic motion. I want to point out to you that we've been discussing position as a function of time. For a simple harmonic oscillator, we say that it's doing something like this, starting at some position and going in a cosinusoidal fashion, an actual sine wave in space. So now we've got something a little bit different. I'm going to try to draw some axes on this and say that this is position maybe in the y direction versus position, let's say, in the x direction. So now, oh man, now we've got different things to define. This distance, this is a distance.